She received all her degrees from UC Berkeley. Then she was an assistant professor at Caltech. Then she is now an associate professor at Stanford. She is a fellow of the IEEE, holds many awards. She is the Brett Faculty Development Scholar Chair at Stanford. And she received the National Academy of Engineering Gilbert Lectureship, Sloan Fellowship, NSF Career Award, ONR Young Investigator Award, and David Grip Memorial Prize from UC Berkeley. She also is very active in the IEEE, including several editorial board memberships, and also the Board of Governors of IEEE Information Theory Society. Today she's going to talk to us about cross-layer design of wireless communication systems.
Thank you very much, Senator. It's nice to be back. The last time I was here was in 1994 for a job interview, and it's much more fun to give a talk when your future employment doesn't depend on whether your audience likes it or not. So hopefully you'll enjoy the talk, but also get a paycheck one way or another. I'm going to talk about cross-layer design, and the sub-theme of my talk, this notion of whether it's better to be robust, quick, or responsive, where that comes from is that in doing a lot of work at different layers of the protocol stack in wireless networks, we know a lot about trade-offs that occur at any one particular layer. And in fact, I've done a lot of work on adaptive modulation, where you're responding to interference and channel conditions. I've done a lot of work on multiple antenna channels, where you can get very high data rates. And I've worked on diversity systems, where you make things very robust. And some of those themes translate to higher layers of the protocol stack, not just at the link layer. But really to decide which of these things you want to be, whether you want to have high data rates or robustness or adapt to your environment, depends very much on the higher layers of the protocol stack. And so, at least in my view, it's no longer enough just to look at one layer and optimize that layer. You have to look at the trade-offs associated with each layer in the protocol stack and go to a higher layer to figure out the optimal point on that trade-off curve to operate. So that's going to be kind of the theme of my talk. I'm going to present that in the context of my vision for future wireless systems. So much of the work that's gone on in wireless since I graduated in 1994 has been really on cellular systems and wireless LANs. But I think that we're seeing a shift away from communication systems that are only about people communicating with other people or accessing information from the internet to more device-to-device networks, where you're going to have a lot more wireless ad hoc networks that aren't necessarily carrying voice or even video, but carrying small amounts of data to do things like distributed control or sensing. And so a lot of the applications that I'm excited about for future wireless networks are more in the realm of sensor networks or automation, automated highways, industrial automation, where it's not so much about high data rates anymore, but you have very severe constraints on your communication system. And that means to a large extent that you need to rethink the way you design these systems. And in particular, what we see are, in the context of automated control, hard delay constraints. So if you've got an automated highway system here, and there's a braking command that's going out from one car to the one behind it, well, there's a very severe delay constraint on that braking command, because if it gets there too late, the cars crash into each other. So the notion of a network crash in an automated highway system is much more severe than when you're trying to download a video clip off the internet. And so rather than think about average delay, as we normally do in networks, when your application is something with a hard delay constraint, you need to think differently about the way you design the network. Same is true under hard energy constraints. So suppose we have a sensor network where we want to drop these sensors, say a building collapses. You want to drop the sensors into the building and find out where the people are, or track the spread of fire or chemicals or something like that. Well, these nodes typically are going to be battery powered, and once their batteries die out, that node is no longer available not only to participate in the network, so it can no longer serve as a multi-hop router, but it also can't sense anymore, so it can't perform its original function. And therefore, when we're looking at hard energy constraints, where these nodes die after some point of time because they've used a lot of energy, it turns out that the way that you think about designing the networks is fundamentally different. And I'm going to touch on that in a couple of different places in my talk. So really, under these kinds of hard constraints, what matters is not so much what's the data rate that we're getting at the link layer, but end-to-end metrics associated with the application, which may be sensing, which may be control. And so that really gives rise to the notion of cross-layer design. Now, some of the challenges in this vision for future wireless networks are, first of all, the channel itself. So the wireless channel is a very difficult communications medium. It's time-varying. In many cases, it has a fundamentally low capacity. It's a broadcast medium, which means that everybody interferes with everybody else. So we can't get the kinds of data rates over wireless channels as we get over fiber. That makes it difficult to support these kinds of demanding applications in wireless networks. Okay, so that's one problem. The other issue is there's a lot of dynamics in these wireless networks. So you've got users moving around, you've got traffic patterns that are changing, the network conditions are changing, and so supporting hard constraints like energy or delay constraints in the face of all of these random variations is a tricky undertaking. Another big issue is the fact that applications are heterogeneous. So we see that already in the internet. You have voice, you have data, you have video, which have different data rate requirements, different delay constraints. And the internet doesn't support those heterogeneous applications very well. It's good at data, but if you've ever tried to do even voice over the internet, it doesn't work very well. Now try doing that over a wireless channel where you have much lower data rates, a lot more interference, randomly changing conditions. It's much more challenging. So how are we going to support these heterogeneous applications that are very demanding given this underlying difficult channel and all the dynamics associated with the network? And finally, as I mentioned before, the energy and delay constraints really change the fundamental design principles. Now, that's great if you're a graduate student, because what it means is that, you know, the last 30, 40, 50 years of work in information theory or communication theory may not apply anymore. You may be able to start with a clean slate because these hard constraints fundamentally change the problem. And it's always good when you're a graduate student to work in an area where there are no results than to kind of come up with the next incremental result of, you know, the 1000th paper on MIMO or something like that. So these fundamental constraints make for a very rich space of problems to look at in research, and we'll see some of that. So really, the notion of cross-layer design is to attack these various problems that I just laid out for future wireless networks. And the idea is that we don't want to get rid of layers. So layering is a good thing. It allows specialization, it allows modularity, it allows scalability. But we want to find a way to avoid negative interactions between layers and leverage synergies between the different layers to make these systems work better. So when I think about layering in wireless networks, there's these 5 layers: the application layer, the network layer, access link, and hardware. And I include the hardware, which is typically not included in an OSI model, because if you're focused on energy constraints, the energy is consumed in the hardware. So if you neglect the hardware, you really can't understand energy consumption in these kinds of sensor networks where you're under severe energy constraints. So the kinds of tools that we might use for cross-layer design are things like diversity. Now, diversity is something that we've understood at the link layer for a long time. You have a fading channel, take multiple antennas or time slots or frequency bands, and you can get robustness against fading in the channel because it's unlikely that on all antennas or in all time slots or in all frequency bands, you're going to have the same deep fade. But diversity doesn't just apply at the link layer. You can also think about diversity in access. So you don't necessarily need to access the network from only one access point. You can have multiple access points and use that as a form of access diversity. Same in the network. You can have multiple routes for the same data through the network, and that way if one of your routes is congested, you're unlikely to have all the routes simultaneously congested. The application can represent data in multiple ways using something like a multiple description code. So that provides diversity at the application layer. So we see that there's diversity that can occur at all different layers of the protocol stack, but if we're going to build in diversity at each layer, we want it to work together between layers, not against each other. Similarly with adaptivity, you can use power control to get around fading at the link layer, but if you increase your transmit power because you're in a deep fade, you're going to cause a lot of interference to somebody else. So the adaptivity that you build into your network shouldn't just be at one layer, but it really needs to cross layers. Okay, so all of the tools that we're used to applying to a particular layer to optimize the trade-offs of that layer, when you think about a cross-layer design, you need to investigate how additivity or diversity or scheduling in any one layer impacts other layers. Okay, so basically what I'm going to show is that substantial gains in throughput, efficiency, and end-to-end quality of service in terms of concrete metrics can be achieved through cross-layer adaptation, through a cross-layer design, taking advantage of some of these techniques. Now, I don't have a grand theory of cross-layer design. It's something I've been working on. It's even in my thesis. So I've been thinking about this problem for a long time. It's a tough problem. Rather than give you the grand scheme theory of cross-layer design, I'd like to focus on a few applications where we can get some insight to see the benefits of cross-layer design and what are the right tools to approach this kind of a framework. So I'm going to look at 3 specific applications. First, I'm going to look at joint source and channel coding in a MIMO system and network. Then I'm going to switch gears and talk about energy-constrained networks. And finally, I'm going to talk about distributed control over wireless networks. Very different problems, very different tools. But we'll see that in all 3 of these applications, the notion of cross-layer design can really provide substantial performance gains. So let's start with the joint compression and channel coding with MIMO. By the way, all of the work that I'm presenting is joint with other people, and I'm not going to name all of them, but usually they're at the bottom of the slide. So, and those are the people that did all the work, and I'm just talking about it. So anyway, for this setting, if you have multiple antennas and you want to send some data over this multiple antenna channel, let's say it's an image, then you can use the antennas for multiplexing. This is the traditional MIMO multiplexing gain. Because we know that if you have n antennas at the transmit side and n antennas at the receive side, then you can actually get an n-fold gain in capacity over just having a single antenna at each end. So one of the reasons why people are so excited about MIMO is these tremendous capacity gains. But the problem is that even though you get these big gains, each individual one of these links has a channel gain that depends on the eigenvalue associated with the matrix of the MIMO channel. So some of those eigenvalues might be quite small, which means that some of these links might be error-prone. So what I do is I use these antennas for multiplexing. That means that I can send a very high data rate through this multiple antenna channel. So my original image doesn't need to be compressed very much. On the source coding side, I can get a very good reproduction of the image because I have a very high data rate on my channel, so I don't need to compress my data very much. So I send this very good reproduction of my original data through a channel that is error-prone. And that means that I'm going to get these white blocks whenever I get an error. Okay, so that's one way that I can use my multiple antennas. Or I can use them in a completely different way, which is for diversity. So now, rather than use these multiple antennas for multiplexing, I'm going to do transmit and receive diversity combining so that I no longer get a high data rate over those multiple antennas, but I get a very robust channel because I'm combining the gains on all the different antennas. Okay? So now I have a very low probability of error on my channel, but I also have a low data rate. So I have to compress the original data quite a bit because my channel doesn't have a very high data rate. So now what happens at the receive end is I don't make any errors, or I make very few errors, but the reproduction of my image is fuzzy because I have to compress it a lot to get it through this relatively low data rate channel. So the question is, which is better? Do I want to use my antennas for multiplexing, or do I want to use them for diversity? And the answer is, you can't answer that question just by looking at the trade-offs at the link layer, because it really depends on whether you want to see this image or this image. It's an application question. You have to go back to the application and say, which of these 2 reproductions are better from the application perspective. Okay? So we can formalize this problem mathematically using a very nice result by Zhang and Shea, which mathematically describes the trade-off between diversity and multiplexing on a MIMO channel. So I won't go into too much about the details of this, but basically the idea is if you have a block-dating channel with block length T, you can define a family of codes for that channel. And given this family of codes, we'll define the diversity as basically the slope of the probability of error curve. So the more diversity that you have, the faster your probability of error is going to fall off. That's what diversity does for you. So the diversity we're going to define is in the limit of high signal-to-noise ratio, the log of the probability of error over the log of the SNR. So that's basically the slope of the probability of error curve. That's our diversity parameter, minus d. And the rate is just the rate that I get with this family of codes over, again, the log of the signal-to-noise ratio. So that's going to be this little r, again, in the limit of high signal-to-noise ratio. And what Zhang and Shea showed in their results is that there's a very simple relationship between the diversity and the rate, which is basically the maximum diversity that I can get as a function of my rate is just m minus r times n minus r, where m is the number of transmit antennas and n is the number of receive antennas. So it's a very simple trade-off curve that looks like this. If I use all of my antennas for diversity gain, then I'm operating on this point on the curve, which means that I don't get any multiplexing gain. I don't get any rate increase from the multiple antennas, but I'm getting a lot of diversity. So my probability of error is going to go down, and that would be operating at this point. Conversely, I could use all of my antennas for multiplexing, and then I get the minimum of the number of transmit and receive antennas. That's how my rate is scaling with the number of antennas, and that will give me this point here. And what they showed is that there's actually a piecewise linear curve between those points, so I can operate anywhere on this curve. I can use some of my antennas for diversity with some rate penalty so that I get a more robust channel, but I don't get as high a rate as if I used all my antennas for multiplexing. So I can operate anywhere on this trade-off curve. And the question is, where should I operate? Okay? So I've got this trade-off curve, but which point do I want to operate on? And you can't answer that question just by looking at the MIMO channel. The MIMO channel tells you, here's the trade-off curve. But in order to figure out where to operate, you have to go to a higher layer of your network to say, well, what's better, diversity or multiplexing, diversity or high data rate?
What
So,
better means here what?
I'm sorry?
What better here means what?
It depends on the antenna metric. Okay, so better means if I say, do I want to have more robustness or a higher data rate,
So
you need a metric.
You have to use a metric, but you do not use the trade-off.
No, the metric will tell you where to operate on
No. The question is very precise. If I have two metrics or three metrics and a trade-off curve,
you may want to operate in a different place.
They will only tell me the trade-off curve. They will not tell me where
No,
to operate.
no. If the metric is defined, say my metric is what is the mean squared error of this image at the output, okay? I will, and I'll show you now, that will tell you exactly where to operate on this trade-off curve. It will tell you exactly what the optimal rate diversity trade-off is.
No. Okay. When I have more than one metric, okay?
Okay, I'm talking about one metric.
There's no optimal. When I have more than one metric, I have trade-off curves of some surfaces.
Right.
And
If you have more than one
if I'm going to
metric,
decide
yeah.
where I'm going to operate is because of other reasons, not reasons that were put into the formulation of the problem. That's why I asked you what do you mean optimal by the high layer.
So to me, there's only one metric associated with the end-to-end system.
Which is?
Well, it depends on the application, and I'll show you different metrics for different applications. In fact, I'll show you the metric for this particular application, which is sending source data over a multiple antenna channel. But there'll be different metrics. For the control application has a completely different metric. The energy constraint system has a completely different metric. But assuming there's one metric, which there usually is for an end-to-end system, there's one metric, be it a cost function or mean squared error distortion or something like that, you can figure out where to operate on the trade-off curve, not only at the link layer, but at every layer. Okay? So let's look at this for one specific example. So in this example, I've got some source data that I want to send. I'm going through a source encoder, which will compress it down to S bits, and that gives me some index associated with the source code. The index assignment will take the S bits, assign them to a source code. That's going to go through the channel encoder, the MIMO channel, and then the decoder on this side, and then we just do the reverse operation. So what's actually going on here intuitively? Well, basically, if I increase the rate of my source code, then I decrease source distortion. I basically have a higher rate source code. But the problem with that is that then, because I'm trying to send more rate over the channel, my space-time MIMO channel encoder has to encode at a high data rate, which means it has less diversity. So I'm going to have less diversity here, which means I have more errors in my channel decoder, and that may give rise to a higher end-to-end distortion. So with this mathematical framework, I can now say if what I care about is the end-to-end distortion, how should I be using my antennas? And that will tell me exactly what the source rate needs to be, as well as what the channel encoder needs to be. So let's look at formulating that problem. Okay, so the end-to-end distortion is the probability that the channel decoder selects the wrong channel code, word J, instead of the channel code I that was sent. So this is the probability of error associated with the channel itself. The end-to-end distortion, then, is going to be equal to the distortion of my original source data minus the compressed source data associated with index J, assuming that I've made a decoding error of channel code J given that I sent on. Okay? So this is the formula, and again, I won't go into the details of this. I'm using a p-squared error distortion metric, which p is often equal to 2, but here it's a little bit more general. Now, the nice thing about this end-to-end distortion, so this is the total distortion associated with both my channel and my source code. And in looking at this formula, it's hard to see how am I ever going to get an optimal channel and source code out of this. But it turns out from a very nice result by Hockweld a few years ago, this end-to-end distortion splits into two pieces. One that depends only on the channel error, okay? So this is the probability of error in the channel. And the other that depends only on the distortion associated with my source encoder, assuming that I correctly decode the channel, okay?
But you get this splitting under very specific assumptions.
Under,
in general, it doesn't split.
For general distortion metrics, it doesn't split, but for the one, or channel models, but for this particular distortion metric, it does split, okay? So it splits into two pieces, and now I'm going to look at minimizing this total distortion, which is now in two pieces. So if, again, I look at the total distortion, that splits into these two pieces, and I can write that down in terms of the source code parameters. So P is the power of the error that I'm looking at, K is the rate of the source, and S is the number of bits. And this term here just depends on the probability of error in the channel, where we have our optimal distortion rate trade-off. Okay, so remember, we're trying to figure out how to use our antennas, and I've already said that this distortion is the slope of the probability of error in the channel. Okay, so that's where that probability of error comes in. Now, if I look at the high signal-to-noise ratio regime, where signal-to-noise ratio is high, basically, when I write this down, I equate the source and channel rates, because clearly whatever rate is coming out of the source code has to be equal to the rate that I'm sending over the channel. And when I equate those two, I end up getting these two expressions as a function of signal-to-noise ratio. So the end-to-end distortion is going to be the signal-to-noise ratio raised to this power, and again, this term depends only on the source code, plus another term, which is a function of my optimal diversity rate trade-off, okay? So now looking at this, you can say if I let my signal-to-noise ratio go to infinity, I have to equate these two exponents in order to minimize the end-to-end distortion. Because if I don't have those exponents equal, as the signal-to-noise ratio goes to infinity, one term is going to dominate the other. And that's not going to be the most efficient way to operate the system. So basically, in the limit of high signal-to-noise ratio, I want to equate the two exponents to minimize the end-to-end distortion. So if I do that, magically, I get a very simple expression for my end-to-end distortion. It just depends on this optimal diversity rate trade-off point on the curve that I showed you a few slides back. Okay? So I get a very simple expression for the end-to-end distortion. And asymptotically, if you look at the log of the end-to-end distortion over the log of the signal-to-noise ratio, we get that's equal to the optimal diversity point as a function of the optimal rate. Okay, so this is the same form that, remember I showed you the D and R expressions from the Zheng and Shea paper. Well, this is in the exact same form. Okay, so we get a very simple relationship for this end-to-end distortion in the limit of high signal-to-noise ratio. And we can also solve this problem for finite signal-to-noise ratio. So suppose I don't let the signal-to-noise ratio go to infinity, then you no longer know that it's optimal to have these exponents be equal. So you have to solve for the optimal operating point. But this turns out this is piecewise linear. This is the formula for the diversity rate trade-off. This is a convex problem, so you can solve it using standard techniques. And the solution shows how to best use the antennas, whether you want to use them for multiplexing or diversity or both. So that's the mathematical framework, and let me show you some numerical results now. So basically here what I'm showing is K is basically the inherent rate of the source. So if K is large relative to my block length, it means that my source inherently has a very high rate that it would like to minimize, to have low distortion. So my source is pumping out a lot of data, which intuitively means you probably want to use your antennas mostly for multiplexing. If the source has a very high data rate, you want to maximize the rate that you can send over the channel. And that's exactly what we see as a function of signal-to-noise ratio. As we use more and more antennas, so this is an 8-antenna system, as I use more and more antennas for multiplexing, my distortion goes down monotonically, except when I use all of my antennas for multiplexing. And the reason for that is because of the asymptotics of this analysis. When I use all of my antennas for multiplexing, I have no antennas left for diversity, so my probability of error is going to go to 1, and I get a large distortion. Okay? Now, the opposite scenario is when my source rate is quite low. So this would be something like a sensor network, where the data being produced is pretty small, so I don't have a lot of source rate, in which case, intuitively, you would expect that most of your antennas should be used for diversity, because you don't need the rate associated with the multiple antenna channel, so use those antennas to get robustness. And indeed, that's what we see. Again, using two antennas for rate, it gives you the minimum distortion. Again, we get a discontinuity if we use all of our antennas for diversity, because we don't have any left to transmit over the channel with. So those are the non-continuous points associated with this mathematical framework. Yes?
What if I plot this in 3 dimensions?
What's the third dimension?
You show me comparisons of the various metrics pairwise.
There's one metric here, end-to-end distortion.
No, you have distortion, multiplexing, and diversity. And if you go out your curves, this one and the previous one, okay, I can make a very good argument where I need to operate, because all my criteria are met between 3 and 5, and all of them are pretty good. When you have 3 metrics, like you have now, you look
I don't have 3 metrics. I have 1 metric.
Yes, you do.
No, I have 1 metric. Okay, my metric is total distortion. I'm only interested in minimizing.
You have diversity, multiplexing.
Those aren't metrics. Those are trade-offs that I can pick how I operate. Anyway, let's maybe take this offline, because I have a lot of other things I want to present.
Yeah,
okay.
When you have more than 2 things to compare, okay?
I'm not comparing. I only care about total distortion. I only care about total distortion. That's the only thing I'm trying to minimize here. And the way I use my antennas is optimized.
Flip back and forth from this in the previous graph.
But that was a different set of parameters. Here I had a different source rate. It's a different, I'm solving a different problem here. The source rate is different. Here, I have a different source rate than in that one. So clearly, again, intuitively, if your source rate is high, you want to use more antennas for multiplexing. If your source rate is low, you want to use more antennas for diversity. But clearly, the number of antennas you use is dependent on the source rate.
But my view explains exactly why you get that knee over there on the other curve, and why you get this kind of behavior here.
You get the knee because there's an optimal number of antennas to use.
Because the other metric hits you. If you go
There's no other metric. There's only 1 metric. Anyway, we'll come back. Okay, so again, if the source rate is in the middle, then you use roughly half your antennas for multiplexing and half for diversity. Good thing it's not a job interview, then I could. All right, so if we look at the total distortion as a function of signal-to-noise ratio, you get this linear behavior, and that's not surprising because remember, I said in the limit of high signal-to-noise ratio, that this is an upper bound now, so it's not exact, but it's upper bounded by that slope of the optimal diversity rate trade-off curve. So we do expect to have linear behavior in the limit of large signal-to-noise ratio. Okay, now what I've shown you so far is very mathematical, theoretical. We can get closed-form solutions or formulate the problem as a convex optimization problem. But you can also do this for real codes. So actually I looked at progressive video encoding by a colleague of mine, Bernd Giroux, where, again, the total distortion splits into source and channel distortion components. I looked at some space-time codes that were published a few years ago that give you the trade-off between diversity and multiplexing. There's actually better codes than these now, but these are the ones that we used. And so you can look at a real framework of a real source code and a real channel code, and again, perform the same optimization. It becomes an integer programming problem because the number of antennas that you use for multiplexing or diversity in your space-time code design is an integer number, and so you solve this integer programming problem. And again, you can come up with the total distortion as a function of the number of antennas that are assigned to multiplexing. And basically, this is parameterized by the signal-to-noise ratio, and the results are, again, what you would expect. When you have a relatively large signal-to-noise ratio, which is this curve down here, you have a robust channel. You have a high signal-to-noise ratio. You don't need to use antennas for diversity. So you use all of your antennas for multiplexing, and the more antennas you use for multiplexing, the better your performance. You don't get the discontinuity here because we don't have the analytical framework where we can't use all of our antennas for multiplexing and still have a probability very small. On the other hand, if we have a lower signal-to-noise ratio, like this green curve, then now you're starting to have a lot of errors in the channel, and so you want to take away some of the rate associated with the multiplexing and use those antennas for diversity. So again, these results are exactly what you would expect. Based on the end-to-end metric of total distortion, it tells you exactly how many antennas to use for multiplexing versus diversity. Okay, now there's some extensions that you can do to this, and one of the ones that we're working on right now is the notion of delay. So in a real network, if a packet is lost, you'll retransmit it. Okay? So that introduces another dimension in the trade-off curve. So if I keep retransmitting, eventually I'm going to get the data through, so my robustness goes up, but my delay also goes up. So now you can look at a notion of having a three-dimensional trade-off curve and do the same kind of optimization, but now in 3 dimensions, because you have 3 different parameters you can play around with. This three-dimensional trade-off curve was obtained by Carrie Damon and El Gamal. It's a paper that's been submitted to the Information Theory Transactions, and I believe it will be presented at the ISIT later this year. So once you have that region, now again you can look at optimizing whatever end-to-end metric that you're interested in. And that's really where a lot of the challenge comes in. What is the right end-to-end metric that takes into account delay in the end-to-end distortion? So you can think of a simple metric where you just say, I have a hard delay constraint. If the data comes in after that delay constraint, then I just assume it's completely lost. You can compute the distortion that way, or you can come up with more clever ways to incorporate delay into the distortion. So this is one of the things that we're looking at now. Yes? So does he have a quote on how many questions?
No, but
we just exceeded it.
I'm not intimidated by that. But the question is this. You just said that this is 3-dimensional, and you just said that it's a 3-dimensional trade-off.
Yes.
So you're treating this as some metric or constraint, right? I mean, you said
no, I'm treating it as a trade-off curve.
Diversity delay.
Look, if I have...
So in what sense this is a trade-off if they're not metric?
Because look, I've got a trade-off curve. I've got some region here, okay? Now, I can operate anywhere on this region.
Just define for me what
but
you mean by
for
trade-off
one
curve.
metric, let me say I've got f of x, y, and z, okay? There's going to be one point in this 3-dimensional curve that minimizes this, okay? So I'm looking at the minimum over the point x, y, z of this function. One function. There's one point. Maybe there's more than one point, but there's at least one point that's going to minimize that if it's a convex region, and that's what I'm looking to find. Once I find that minimum point, that tells me where to operate. So this trade-off curve is associated with my design. I say, okay, I'm a MIMO channel code, source code designer, okay? I can give you multiplexing or diversity. What do you want? Well, you've got to look at the metric associated with that trade-off.
Hold it. I just want to understand in which way you use the word trade-off.
This is inherent to my design at the link layer.
What do you mean by trade-off? What I understand by trade-off, I give up something here and I gain it somewhere here.
So you give up data rate to get robust.
Right. So that rate is something I care, I measure. I'm trying to make it large or small, right?
No. So this is the point. Data rate and robustness are components that affect my end-to-end metric in different ways. And there's a trade-off. I can get high data rate for robustness or vice versa.
And you don't call this metric, so you don't
No, they're not. No, they're trade-offs. They're inherent trade-offs to the link layer design.
Okay, we'll come back to that.
Okay, good. Be an interesting one. All right. So let me move on, now that everybody's happy, more or less, to ad hoc networks. So let's make the problem more complicated. So far, I've only talked about a point-to-point link. But you can see the same kinds of trade-offs in an ad hoc network. So you can say, here I've got peer-to-peer communications, I've got multi-hop routing. What kinds of trade-offs can I associate with the design of this network and then go ahead and perform my optimization? So let's look at some problems with respect to the ad hoc network. Now, some earlier work that I did with a student defined a capacity region slice for these multi-hop networks. It's an achievable rate region. It's not the capacity, the Shannon capacity. But it basically tells you if I take a network, say a small network of 6 nodes, the capacity region for a 6-node network is 30-dimensional because every node in the network can talk to every other node, so I've got a 6 times 5-dimensional region. So these are very complex regions, but you can come up with a capacity region, 30-dimensional capacity region for this ad hoc network. And this is a 2-dimensional slice of it where I say I've got nodes 3 and 4 are talking to each other, nodes 1 and 2 are talking to each other. All the other nodes in the network can be used for helping these 2 sets of nodes to communicate, but they don't have any data of their own. Okay, so that's the slice I'm showing you here. And then you can assign different capabilities to the network. So you can say, I'm not going to do any spatial reuse and only single-hop routing. And that will give you this line down here. If you add multi-hop routing, then you get a higher capacity, and it actually jumps up to here. If in addition to multiple hops you do spatial reuse, you get a higher capacity. You can add power control to that. You can add successive interference cancellation. You can keep adding capabilities of the network, and your capacity region is going to expand. This is a TDMA network, by the way, so that otherwise it gets very complex to analyze it. Now, I'm not going to focus on this capacity region because this is old work, and because we don't care about capacity, we care about trade-offs. So this doesn't tell me anything about how robust any of these links are. It doesn't tell me anything about the delay associated with these links. So what I'd like to look at is the same kind of set of trade-offs, but now rather than focusing on a point-to-point link, focus on a multi-hop network, okay? So now I'm going to have the same kind of delay, throughput, robustness across multiple layers as I did in that single point-to-point MIMO channel. So in particular, I can, if I have data I want to send from A to B, I can send that data over 2 separate routes, okay? Now that's going to make that transmission more robust, because if one of those routes is congested, then the other one is less likely to be congested. So I'm going to have more robustness, lower delay, lower probability of packet loss. But I'm losing rate by doing that, because I could send new data over the different routes rather than the same data. So you see that there's this trade-off between the data rates that I can get and the throughput and robustness. Same as at the application layer, I can use the same description that I send over these 2 routes, or multiple description. And so we see the same kinds of trade-offs associated with the point-to-point link in this ad hoc network. And the question is, can we optimize the optimal operating point for these trade-offs to minimize the end-to-end distortion? Now, this is a very complex problem, and I'm just going to present some recent work that I've done with Bernd Giroux and several of our graduate students on a framework for looking at this complex problem. Again, there's a lot of interesting challenges. There's a lot of information theoretical results buried in there, but this is just one set of solutions. So the idea here is that starting at the link layer, I can use any set of adaptive techniques that I want to come up with the capacity region that I showed you 2 slides ago. So say I do adaptive modulation, encoding, and successive interference cancellation, power control, whatever I want to do at the link layer. That will give me a capacity region, okay, which tells me the rates that I can get from any one node to any other node in the network. Now, once I have that capacity assignment, what I'm going to do in my routing protocol is route traffic over those links. And the closer I operate those links to their capacity, the higher the delay. So this is the problem when you're looking not at capacity, but I'm actually trying to get data through a network. Capacity is fine, but if I try to operate close to capacity, my delay goes up. Okay? So basically, my routing is going to decide how to route traffic based not only on the capacity of the links, but the delay constraints of the data, Where does the delay constraints of the data come from? Well, that's going to come from the application layer and the transport layer. So basically, the idea is that I have something that's called a rate distortion preamble associated with all of the data coming down from the application layer. And that rate distortion preamble tells me for each packet, if the delay, given a distribution of delay, how much distortion those delays contribute to the end-to-end distortion metric. So I may have some packets that it doesn't matter how delayed they are, okay? Those packets, my routing protocol is going to send over links that are operating close to capacity because delay doesn't matter. On the other hand, if I have data that's extremely sensitive to delay, which is captured by this rate distortion preamble, then my scheduling and routing algorithm is going to send that data over links that are relatively lightly loaded because they don't exhibit much delay. So this is a very complex set of protocols, truly cross-layer because everything is interacting with everything else. So the question is, how much do you gain from this? And it turns out that you gain a lot. So what I'm showing here is in purple is what you would get with what we call oblivious layers. You just use the protocols that are optimized for a particular layer, but there's no cross-layering going on. And we look at both one-path and three-path routing. So again, the three-path routing is going to be more robust to congestion, but it's going to have a lower end-to-end rate through the network because you're sending the same data over three paths instead of just one. And the purple lines are what we get with, the red lines are what we get with our protocol. The black line is what you would get with the perfect network. So if the network didn't introduce any delays or packet loss, that's how you would do. And we see that basically, at low rates, everything performs pretty much the same because there's nothing constraining the system. As you push the rates higher and higher, these oblivious layer protocols fall apart, okay? And it turns out, interestingly, because it's not clear as you push rates higher whether what's going to kill you is the rate limitations or the congestion. And we see from these purple lines that, in fact, it's the congestion that hurts you because the setting where you're only going over one path, which means you have a higher end-to-end rate through the system, falls apart sooner because of the congestion associated with just going over one path. Whereas if you do three-path routing with the oblivious layer, you track the optimal performance for a longer period of time. But at some point, at some rate, that goes down. Yet our protocols where we're doing the cross-layer continue to go up until very high data rates. So basically, we see that we get a threefold increase in data rate for a fixed PSNR, which is the end-to-end distortion metric, or we get a 5 dB increase in PSNR for a single rate. So there's significant gains associated with this cross-layer design. Again, this is very complex. I'm not saying that this is what we would want to build into an ad hoc wireless network. Because of the complexity, this is also assuming central control and everything known. But it does give you some ideas of the benefits of doing this cross-layering. Okay, so now I want to switch gears and talk about energy-constrained nodes. So this is a completely different topic. Now I'm going to say my nodes are battery-powered, and the batteries eventually die out. And that means that each node can only send a finite number of bits. Now the transmit energy is minimized by sending each bit very slowly. Okay, so I minimize transmit energy by using as long a time period as possible to send my bits. That's a problem if I'm doing multiple access, because every node wants to send over an infinite time. I'll get to multiple access shortly. But just for a single transmitter, this is going to introduce a delay versus energy trade-off, because I have to wait longer to get the bits, but it costs me less energy. Now, for short-range networks, it turns out that the processing and circuit energy is on the same order as the transmit energy. And the interesting thing about that is that the longer I leave my circuit on, the more circuit energy I consume. So on the transmit energy side, I want to maximize my transmission time. But from a circuit energy perspective, I want to minimize my circuit energy, the amount of time my circuit is on. So what that means is that first, sophisticated techniques are not necessarily energy efficient. So all of this turbo coding and MIMO techniques and multi-level modulation, maybe that's not what we want to do here. Maybe we want to use something very simple like on-off keying. And from an energy constraint perspective, that's going to be the optimal way to communicate. And that's very interesting because, as I said, it kind of throws out the last 50 years of comm theory where we've been pushing for higher data rates but consuming more circuit energy in the process. In addition, you want to turn off these nodes. So if they're consuming energy just by being on and listening, you want to shut them off. But that very much complicates networking because if a node is turned off, it can't participate in the network. You have to figure out when to turn it on. You have to make sure that there's enough nodes around it that if you're doing something like sensing, that one of the nodes in the vicinity will sense if something happens. So this whole notion of sleep modes creates this whole optimization problem, which is really widely an open problem. So really this changes everything about the network design, and I'm going to show you some numerical results which give a very different picture from the way we're used to thinking about ad hoc network design. Okay, so I'm not going to go through the mathematical details of how these numerical results were generated. Basically, we're formulating these problems in general as a convex optimization problem where we're trying to minimize the total energy. That would be subject to some constraints like the maximum transmission time per bit or the peak power constraint or whatever constraints you want to formulate, you can put into this framework. And again, I'm not going to go through the details. I'd be happy to talk to people offline about it. But the bottom line is that you can formulate all of these either as convex optimization problems or use relaxation techniques that make non-convex problems convex. Okay, so let's first look at modulation optimization. The idea here is that I want to optimize the amount of time that I transmit along with my constellation size to send a fixed number of bits. And what you see is that if you're going over a long distance, like 30 meters, transmit energy is going to dominate. So you want to transmit over the maximum duration of time that you have available. On the other hand, when you go to smaller distances, like a meter, now your transmit energy no longer dominates circuit energy consumption. So basically what you want to do is blast out your bits, typically using a fairly high signal constellation, and then turn off your transmitter. Okay? So you see that the optimal transmission time goes down as the transmit distance goes down. Now, what about coding? We know that coding is going to save transmit energy, but it's also going to cost processing energy. So the question is, should we code or should we not code? It's not clear. So what I'm showing here is an optimized coded system in red, which means that I'm not only using the coding, but I'm optimizing the constellation size along with it. The reason that's important is that if you're using coding, you can use a large constellation, blast that out really quickly, use your coding to decode it with relatively small transmit energy, and then shut everything down. Now, if you look at a coded system where you're not optimizing the constellation size, it turns out that that does worse, that's the green line, than an uncoded system with the constellation optimized. So basically, there's a trade-off between if you only optimize coding or constellation size, coding is not good at small distances. But if you simultaneously optimize the constellation size and the coding, then in fact you get a 90% savings with coding down to very small distances, down to a meter. So that means, again, cross-layer design, you're optimizing both the coding and the modulation, as well as the transmit time associated with this transmission. Okay, now what about routing? All right, so if we know that if I want to do multi-hop routing and I'm trying to minimize transmit energy, then the best thing to do if node 1 wants to send to node 4 is to go through these intermediate nodes. That's going to minimize transmit energy because of the fact that power falls off with distance raised to some power. But now if I take into account processing energy, these nodes have to burn up some processing energy to process the packets that they're forwarding. And it turns out that, in fact, you want to do single hop routing in this case because the processing energy associated with using these nodes dominates the transmit energy savings that you get. Not only that, but there's also an optimization of the time duration of the transmission. So here I say that I can transmit over 1 unit of time, but I'm only using 0.3 units of time because that's optimizing the link layer as well. Now, what if, so the interesting thing about this is that multi-hop routing may not be optimal when you take circuit energy into account. Again, completely different way of thinking about routing than any paper that you'll find on multi-hop routing that is typically only looking at transmit energy. Now, what if the relay nodes also have data descent? Then you get a very interesting routing protocol where some of the time you transmit single hop, some of the time you transmit multi-hop. Again, the duration of these transmissions are optimized, so you can think about that as a multiple access protocol. What's the optimal amount of time to assign to each node for its transmission? And if we also do link adaptation in terms of optimizing the constellation, we get another 70% of energy saving. So again, this is truly a cross-layer design looking at the link layer, the MAC layer, and the routing. And it's very different routing from what we normally expect. Okay, another thing that we've been looking at in this energy-constrained context is the notion of cooperative MIMO. So if all of these nodes just have a single antenna, they can exchange information to form a multiple antenna transmitter. And on the receive side, they can exchange information to become a multiple antenna receiver. So we've already seen that multiple antennas at the transmit and receive side are a good thing, but there's some cost associated with this cooperation, both on the transmit and the receive side. So let's look at the benefits of this cooperation. First, from a capacity perspective. So basically, if I have these two nodes that have data to send to these two nodes, I'm going to define the gain between the nodes and look at the capacity associated with this cooperative system as a function of that power gain G. Now, if there was no cost of cooperation, then basically you would see achieving this upper bound associated with the MIMO system. Because you can think of this as a two-antenna transmitter, two-antenna receiver if there's no cost of cooperation. Well, it turns out that we can achieve that upper bound. The best we can do is looking at this as a multiple antenna broadcast channel. So we don't really know, because these nodes are basically receiving the same, almost the same transmitted signal with a slightly different noise because they're close together. It turns out we can't get the benefits of receive cooperation, but we can get the benefits of transmit cooperation. And we can approach that broadcast channel upper bound associated with doing dirty paper coding on these two nodes if the gain G is sufficiently large. If it's not sufficiently large down here, then basically we're better off not doing cooperation and doing a time division strategy between the two. Okay, so that's for a topology where the nodes on both the transmit and the receive side are very close together. But in fact, this cooperative gain is going to depend a lot on the topology. Because basically what happens is, suppose these two nodes want to send data again to these two nodes. Well, if this node is close to this node, then you can see that having them talk to each other to cooperate is probably the right strategy. So they exchange data, they do dirty paper coding. But as this node moves closer to the receive end, it's starting to look like you probably want to use it for a relay. Because the cost of these two nodes cooperating as this one moves farther and farther away is going to go up. And it turns out that doing that kind of cooperation is suboptimal relative to just using it as a straight relay. And that's what we see in these capacity curves. So basically we see that cooperative dirty paper coding, where these two are exchanging information, they form a multiple antenna broadcast channel, use dirty paper coding, is optimal up to some distance r, which is a little bit bigger, is around 0.8 actually. So this guy is pretty close to the receivers, but at some point, this is close enough that the cost of that cooperation goes up, so that capacity curve falls off, and it turns out that the cooperative dirty paper coding is the worst thing to do, and just flat relaying, which is this blue curve, is the best thing to do. So again, whether you want to, yeah, okay.
In cooperation, you mean you send the index of the code from one user to the other? Is that what it is?
Actually, you exchange the data. That's our form of cooperation. So you have to have the capacity on this bidirectional link sufficient to support the rate that each node wants to send. And then when they have the data, they can do the dirty paper coding. I don't think you could do just the index of the code in the dirty paper coding framework because of the way the code is structured. I don't think you could just exchange indices. Okay, so the capacity gain depends on the topology. But again, that's just a point-to-point link. So what about now in a multi-hop network setting, where we want to do cooperation both in terms of having the nodes talk to each other as well in forming multiple antenna transmitters and receivers, but also on the routing side. So here we've looked at a specific topology where basically it's a double string topology, and we're going to use an Alamuti cooperation scheme where the nodes actually don't even need to exchange information to do their cooperation. And the idea is, here's my source node, okay? It sends something out. I'm assuming everything's synchronized. So it's going to send out its data, and both of these nodes are going to receive the data. Now, if they know a priori that that this guy is number 1 and this guy is number 2, they can form a 2-antenna transmitter using an Al-Moody scheme without ever exchanging information. Okay? So these two nodes form a 2-antenna transmitter. They use the Al-Moody scheme, and that's going to come in to these two nodes, which do the same thing. So basically, every one of these pairs of nodes forms a supernode, which is a 2-antenna transmitter using the Al-Moody scheme. And the nice thing is that we don't need to exchange any local information. Now that tells you what the transmission scheme is, but I still don't know how many of these nodes should I use. So what's the routing protocol? All right. So now I have to figure out, given that each one of these supernodes can form a 2-antenna transmitter, do I use all of them? Do I just use some of them? So basically, what I'm going to show performance results for is optimizing the link layer, which is the size of the constellation, the transmission time associated with each transmission, and the routing, which is which hops to use. And we see, interestingly, that for minimum energy...
What's the map that you use here?
I'm sorry?
What's the map you use here?
It's time division again, and I'm optimizing the amount of transmission time associated with each transmission, same as in the other prior slides. So if I only look at transmit energy, I basically skip every other node. And if I look at transmit and circuit processing energy, basically I'm only using the first node, and then I go directly to the transmitter. That's in contrast to if I did do cooperation. We see here from a transmit energy perspective, again, you're using every intermediate node to do your routing, so you get a very messy picture. And with circuit energy, it looks like that. And I want to show, I'm not going to talk about the delay scheduling, but let me just show the performance results. So basically, interestingly, what we see is that with non-cooperation and no optimization of the constellation, we get this curve. If I do my cooperative MIMO and optimize the signal constellation, I save both on delay and energy. But again, the modulation optimization is a key component of this, because if I don't do that, I'm actually quite close to the non-cooperative realm. Okay. I just want to briefly touch on the idea of cooperative compression, because if these nodes are exchanging information to communicate, if they're sensor nodes, all of their data is correlated in space and time, so they really should be doing cooperative compression as well. But there's a lot of open problems in this area. So this is some work that we presented at ICAST last month, which is suppose we have an analog source, and that's being transmitted to a bunch of sensors with some noise. And those sensors are sharing a multiple access channel to send that data to a fusion center. Well, we actually know very little about optimizing this very simple problem. First of all, we don't know if we should do analog or digital. So if it was just one Gaussian source, one sensor, then actually analog is optimal. All right, you don't need to digitize and encode. But now that we have multiple sensors, we don't know if analog or digital is optimal. If we do analog, is there a way to do compression? Is there a way to do multiple access? These are all kind of open questions. Should the sensors cooperate in transmission and reception? It seems that they should, because they're all trying to send basically the same data with slightly different noisy versions of it. Okay, so if they should cooperate, how should they cooperate in both the compression and the transmission side? And then also there's the transmit power optimization. So just to give you one snapshot, if we do analog, it turns out we can get more sensors in the same bandwidth. So analog with 20 sensors gives us the minimum distortion. Analog with 10 sensors is the next best one. And digital with 10 sensors down here has a trade-off with the analog side. So these numbers, and again, they're very preliminary results, but they're basically saying, we don't really know. Should we do analog or digital? If we do analog, what's the right way to do compression? How do we compare analog to digital, given all the sophisticated techniques we have for digital and not analog? Okay, so the key message is that these wireless ad hoc networks impose trade-off between rate, power energy, and loss delay, and I just want to take another couple minutes to talk about how these trade-offs impact distributed control. So the idea in this setting is that packet loss or delay clearly is going to impact the controller performance, but there's little methodology to characterize this impact. Basically, if I sample my control system quickly, then on the control side, I'm going to get better performance because I'm sampling very fast, but that's going to burden the communication network. So how do I want to sample my control system, well, you have to understand how packet loss and delay affects the controller, and there's no methodology in the control theory literature to deal with packet loss and delay. So let me just touch on a few of our results in this area. We've actually looked at a system where, so we have a system that we're trying to control. The data coming out of the system, so the system state is transmitted over a lossy channel to a state estimator. That goes into a state feedback controller, which is sent over a lossy channel back to the system. Now, if there were no losses in the system, this structure is optimal for LQG control. But once there are losses, it's not obvious that this is the optimal control structure. Well, we've proven that this is optimal, but now the state estimator is a modified common filter, where the modification depends on the loss probabilities, and in fact, the error covariance of the controller is now going to be stochastic, because it will depend on when you actually lose packets. So basically, we've derived the optimal controller for this setting, which means we can actually now go back and look at the communication system design. So in particular, you can show when the system is stable, and clearly that stability will depend on the packet losses, lambda 1, lambda 2, and lambda 3. Well, now going to the conf system design, suppose there's a set of lambdas where I can maintain stability in my system. Well, I can allocate resources to these three channels, because they're all sharing the same bandwidth and interfering with each other. I can allocate resources to make sure that as long as there is a point, given my network resources, where these lambdas maintain system stability, I can operate at that point. So once you have the controller design, which tells you which packet losses are acceptable to maintain stability, you can go in and design your communication network. Okay? And, okay, I won't go into the analysis of that. So you can view this controller design as the top layer, the application layer, of an end-to-end network, where now the bottom layers are the things that I'm more familiar with optimizing, and now we can go in and optimize these different layers, the network, the MAC, and the physical layer. And I'll just show you, we looked at this for an inverted pendulum on a card, and I'm just going to show you, an iterative cross-layer design, where we're looking at optimizing first the modulation, then the MAC, then the sample period of the controller, and then we go back and re-optimize the modulation. So there's a couple of surprises here. One is that generally coding doesn't help. So you would think that in a control system you would want to code because that makes it more robust. But it turns out that by coding, you lose data rate, and so you're actually better off having the higher data rate and not doing coding. So that comes out of this picture here. We assumed a CSMA MAC protocol. Turns out time division is better because everything's being sampled on a regular rate. But for CSMA, you can optimize the channel access probability. The sampling period, again, if I sample with the low period, your controller performance is better, but you're burdening the network more, and so you're going to lose more packets. So it turns out the sampling period is somewhere in the middle of the range of sampling periods, and then we go back and optimize. And the last performance curve I'm going to show is that given our optimal controller, we can actually maintain system stability in scenarios where we can't with the traditional controller that doesn't take into account the packet losses. So this is really significant. It means that, again, coming up with an application that's robust to what's going on in the network can really make a huge difference in terms of the end-to-end performance. So let me just say a couple of philosophical things here. I'm a cautious advocate of cross-layer design. We've seen from my performance results that you can do a lot better, that sometimes you can maintain stability in a system where you can't otherwise, and you can get orders of magnitude bigger performance gains. But cross-layering gives you higher complexity and less insight, and that's a problem when you're trying to build large systems that are scalable. So I think there's a lot of open questions, like, are there simple solutions? I've presented a lot of complex solutions. Are there simpler solutions? Are there theorems that give us separation, at least between some layers, so we can focus on 1 or 2 or 3 layers rather than all the layers? Or are there separation theorems that tell us if these 2 layers just agree on one parameter, then that's sufficient and they can then be optimized separately? What asymptotics makes sense in this setting? If we're going to do theorems, typically we need asymptotics, but is it signal-to-noise ratio that's going to go to infinity? Certainly it's not delay. in a control setting. Certainly it's not signal-to-noise ratio in an energy-constrained setting. So what are the right asymptotics to use for these different problems? And so those are some of the open questions. And I think there's just a lot of different ways to address this. You can look at it from an information theory or a theorem-proving standpoint. You can just take a particular example of a problem and try to solve it. You can do some simulations. You can build systems. We have very little insight into any aspect of this problem, so there's a lot to do. So let me just end with where I began. Is it better to be robust, quick, or responsive? Depends on the end-to-end performance metric, typically one, and then you can figure out the trade-offs. And all layers have to contribute to the debate because there's trade-offs at all layers, and those trade-off curves are interacting to minimize or maximize this end-to-end performance metric. And I'll end with a plug for my book, Wireless Communications, which is coming out in August. I just sent off the copy edits today by FedEx, actually, before I left on the airplane. So book's available online. You can download it, and it'll be out in August. Thanks.
Thank you very much. Additional questions?
Yeah, in fact.
Yeah, my question is related to Dr. Harris. Like during the previous slide, you said just typically one method
Yes.
for the application layer.
Uh-huh.
Then by choosing this single method, basically the application has already decided on the trade-off. Like in your example, you are optimizing the importance. So you have no choice whether you trade off diversity for the rate. So the problem is not about trade-off, but more like given the trade-off curve, how do you interpret it? Interpret like every point, what does every point mean?
Okay.
Then the application can choose which point it wants to operate.
Well, so different applications will have different metrics, okay? So if you're talking about a control metric, it's going to be H infinity norm. If you're talking about image transmission, it's going to be mean squared error or p-squared error. Very different metrics. Those different applications will operate at different points on the trade-off curve optimally, okay? So that, again, is arguing for cross-layer design because it's saying, suppose I have two space-time codes for my MIMO channel, all right? Well, one of those is going to be optimal for the controller, and one of those is going to be optimal for my image compression. Now, again, is it desirable to have two different space-time codes at the link layer? It depends on how important performance is and what the performance gap is. But if you could switch out the space-time code, depending on the application, then you would want to use two different codes. So that's really the theme here. I mean, again, it goes back to exactly these 3 points. So the trade-offs at each layer, or at any one layer, will tell you different things that you can do, right? For a given application, all right, and a given set of layers, there will be an optimal trade-off point with respect to one metric. But different applications will have different metrics. That's a problem because networks don't like to be designed that way, right? You'd like to have a static design for each layer, use one code, one routing protocol. Now, that's very inefficient, and your performance is going to suffer tremendously. So this is really the heart of this question of cross-layering. We know that there's significant performance gains to be had by optimizing which space-time code that we use and which routing protocol that we use. But there's complexity issues associated with doing that. Can we adapt fast enough? You know, so these are really at the heart of, should we do cross-layering? And if so, which form should it take? You know?
I got to say something, and I don't want to offend anybody, but I have to say, okay, there's a whole field which is called systems engineering, which is trying to understand components of systems, hardware, and layers are a way of doing components, which is, in my opinion, is archaic. It was designed for different networks. It wasn't the
Layering was designed.
The way layers would use them, and everybody else calls them layers, were defined for a particular system requirement where the system is a network, but they were good for wireline networks. I am not convinced at all that they are appropriate requirements, the appropriate structure for wireless. I think you verify that. And therefore, one has to look from scratch. System engineering for wireless, even the layers themselves are not holy. I can give you examples where people are routing already, and you know them. For instance, network coding attacks that particular issue. So I think we have to go back and look at what are the requirements, yes, from applications, so on and so forth, what are the metrics, what are the specifications, what are the trade-offs, and then we'll have a much better picture. Okay. Trying to link the current layers with various kinds of schemes is interesting, but it's not addressing the fundamental question.
Well, I think that if you make the layers abstract enough, and you make the cross-layering coupled enough, you know, what is a layer, really? I mean, so I agree with you completely that we need to think about this in a broad way. I also think that for some networks, you're never going to have cross-layering. You look at the internet, you're never going to touch TCP/IP. On the other hand, you go to an ad-hoc network or a sensor network where it's completely self-contained, it doesn't need to interop with anything else. There you can completely start from
But my
scratch.
claim is the theory, because you did say something, since I'm a controls person, right? That you challenged me, right? So I'm telling you, there is theory that's being developed that is trying to address this question for very complex systems, including networks, in a very systematic, mathematical,
But I'm not sure.
computational way,
Okay,
right?
okay, but I'm still not sure that
But it does not
addressing
start from these are the layers, let me link it.
Okay, let me get it.
Okay, let me take you in a different reality. When you mentioned TCP/IP, the reason why you cannot touch them is because the minute you introduce a layer like IP, you created a market. You created an economy.
Right.
Here, in your area, the minute you have a producer that produces a layer that markets it, you can no longer touch it. So your cross layer is going to go down the drain, not because of the technical issues that you described very nicely here, but actually because of the market.
But what if you're building a standalone network? Then you can do whatever you want, right? I mean, if I'm selling
most definitely, but let me ask you, how many standalone networks with different protocols do we have nowadays?
But I think that for some, yes, but, well, okay. And that's getting into a broader issue.
Right.
I agree to some extent I agree with you. On the other hand, for a self-contained network in a home, there's no reason why it needs to interoperate with anything else, okay?
But there are economies of the scale.
There are economies of scale, and that's what doomed the initial wireless LANs.
That's right.
But if you can come up with something that has 10 times better performance, or that keeps your cars from crashing into each other when the standard doesn't, there may be a market. So, I mean, there's certainly more complex issues than just the technology.
But these
right?
metrics have to be put in the design.
But
No, not anymore.
But I think, again, for a sensor network, it doesn't need to interoperate with the economies of scale are an issue. But again, if you build the right cross-layer design network.
Well, speaking about sensor networks, one of the reasons why we have a real good chance to deploy sensor networks is because of the fact that the standard sensors and standard chips are so small. So cheap. So, for example, the processor in your mouse, which is a standard processor that we use in a sensor, costs half a cent.
Yeah.
So the sensor itself might cost 10 cents. But that's because we have economies of
Right,
scale.
right. And I still think that layering is useful as an abstraction. I mean, you don't want to be religious about the layers, but seriously, I mean, you're not going to get one person that understands everything going on at every layer in a complex network. And so even just to get all the people in the room talking about how this end-to-end network is going to work, I think there needs to be some abstractions of functionality. Call that layers or call it something else.
So let me make an announcement. We will have a roundtable discussion today at 2, between 2 and 3 p.m. downstairs in that little building.